and this is your same slide as you did in chapter 1. You have hopefully already gone through it, but I'm just repeating that now you are trying to make the bicycle frame. If you take steels and alloys, low cost but heavy, corrosion will be an issue. If you take wood, it is light and strong, but it cannot be shaped into the curves and so on very easily. If you take carbon fiber reinforced plastic, it will be very light and strong. There will be no corrosion, but it will be very expensive. If you take aluminum alloys, they will be light, reasonably strong, corrosion resistant, but expensive. And if you take titanium and magnesium alloys, they will be slightly better in properties than aluminum alloys, but more expensive. So you see, except wood that perhaps cannot be properly shaped into all the frame shape that you want, all the other choices of materials are possible and good. That is how engineering works. When there are many possible types of materials, now how do you select? So you see, read at the base, if cost is important, select a steel. It will be really strong, but it will be heavy. So you see, cost is okay. If we want all normal workers and so on, you see around the university campus, all the maintenance people and so on, they travel from one place to the other using these bikes. So maybe 50, 60, 70 reals, 80 reals, and the bikes is there. But if say the properties are really important, we have to go for mountain biking, we have to go to rough terrains where the bike will be subjected to big loads, or we have to take part in cycle races, then the properties are very important and the cost can go high. So we can go to carbon fiber reinforced plastic, right? So this is it about material selection, that for any one product, I can give you another example. Take a car. See, there are Chinese cars, Geely and so on. There are Korean cars like Kia and so on. And then you can even use BMW and Lexus and so forth, Mercedes. Or you can even go to custom ordered cars like a Rolls Royce. A car is a car. And even the lowest quality car is, guaranteed, warranted for 3 years, 4 years, 5 years, 6 years. So it is not a bad property, right? But if you can spend a lot of money, then we can really make things of much higher quality and lasting much longer. So always, what properties do you want? What type of performance do you want? How much life do you want to spend? How much beauty do you want in there? So in all engineering applications, these different types of choices are there. And unless you know the properties and the cost and other things of all of these materials, steels and alloys, CFRPs, aluminum alloys, titanium alloy, unless you know them, then how can you select them in a good manner? Let us now start the main topic. The first major topic, as you can see, is stress and strain in metals. Before we go ahead, I just want to share with you something. Many of you, when you do material science, at the same time, you also register for solid mechanics or mechanics of solids. And some of you who are late in doing material science, rare, but some of you have already completed the course on solid mechanics. Why am I mentioning that? In solid mechanics, there is a full chapter on stress and strain. Usually, it is not a policy to repeat the same topic in a different course. I would always say that, you see, you have covered it in another course. So let us please just go ahead and do it. But here, if you have taken solid mechanics now with this course, then I don't know if the topic of stress and strain has already been completed or not. And without this topic, we cannot go further. That is one thing. The other is that all mechanical properties depend on the concept of a stress and a strain. So even if you are doing it in another course, a very small amount of time spent on a stress and a strain will be useful, and most probably the examples and so on that we will be doing will be different. So now, under a stress and a strain, the first subtopic is elastic and plastic deformation, because all these stresses and strains will depend on whether the deformation is elastic or plastic. If I ask you what is elastic, what is plastic, your answer would be very right if you say elastic is a type of material. You see, rubber band type of material is called elastic, and plastic is a type of material. Many polymers are called plastics. But here, this is not the meaning. This elastic is not the material that is called an elastic. It is not the material that is called a polymer or a plastic. When a body is deformed, when you apply enough force on a body so that some deformation takes place, this deformation can be either elastic or plastic. Because you have done earlier courses in science and so on, you have done some physics, so most of you already know this definition. The definition of elastic and plastic depends on whether we have removed the force after application or not. See, this is very critical. Whether we have removed the force after application or not. We apply force. We apply some force on a piece of metal, nothing happens. We apply more force, nothing happens. We keep on applying force until it starts to bend. So now there is some deformation going on, right? So you keep on applying force until some deformation takes place. Now, when you see that some deformation has taken place, then you remove the force. After removing the force, if all of the deformation goes back, the material goes back to its original shape and original dimensions, then the deformation was of an elastic type, right? And if once you remove the force, some bending still remained, it is not straight anymore, there is some permanent deformation, then the deformation is called a plastic deformation, right? So here, elastic and plastic are adjectives for deformation. When you apply enough load to deform a material, and after that, when you remove the load, if there is no permanent deformation, it was of an elastic nature. If the deformation remains permanently there, it was of an plastic nature.